So welcome everybody. This is April 8th, and we are going through Calculus 1. So we have our warm-up here. We have a question about finding the tangent line, and we have an inverse trig function in there. So this is something that would appear in section 2.6 in our book. So we'll do this today, and then we're going to move on to section 2.7. So the first thing that we see is I've added some information. So the question was, on the equation of the tangent line to f of x equals 2x times arctangent of x plus 1 over 5 at the point negative 1, 0. So if we're finding the equation of a line, we remember that there's two pieces of information that we want. The first one is a point, right? So we always want to know if I have a point and I have a slope, then I can find the equation of a line. And so the point here is given to us, negative 1, 0. So I already have that. I didn't have to do anything for that information. But the slope, I do need to, I do need to do something for this information. So I need to find the derivative of f, and I need to evaluate it at negative 1. So if we're only interested in this value, if the only thing we're interested in is the number, we could use a calculator. Lots of things will tell us what this number is. But for our purposes here today, what we're going to do is we're going to go through taking the derivative so we can practice those derivative rules, and then we'll plug in negative 1 and see sort of what we get. All right, so when I'm taking the derivative, the first thing that I want to recognize here, I always start to think about the structure. So we have two functions, right? So we have our 2x times arctangent. So immediately I'm thinking this is product rule. So I have a 2x is going to be my first function, arctangent of x plus 1 over 5 is my second function. But then also inside of that, I'm going to have a chain rule. So when I take the derivative of my second function, arctangent, I'm going to have to take into consideration that we do have this inside function here, and I'm going to have to use chain rule on that one. All right, so let's go ahead and I'm going to set up, so I said product rule. So we'll set up our parentheses, so our framework to do product rule. So I'm going to have my first function, okay, which is 2x. I'm just going to leave that alone. Now I have to multiply by the derivative of my second function. So we remember that the derivative of arctangent is 1 over 1 plus that inside function squared. Okay, so we have this, and we're going to put in x plus 1 over 5 here. And then I have to multiply all of this by the derivative of my inside function. And x plus 1 over 5, that's a linear function with slope 1/5. So the derivative of that is 1/5. Okay, so this is the first part of my product rule. And then we'll flip it around. I have to take the derivative of my first function. So the derivative of 2x is 2. And then I can finish by just leaving this alone. So I get this here. Now, so this is my derivative, and what I want to do is figure out what happens to this when I plug in negative 1. All right, so when I plug in negative 1, hopefully something nice happens. All right, so f prime of negative 1, this is going to be 2 times negative 1, which is negative 2. Okay, so when I think about this, really what I'm doing is I'm plugging in negative 1, right? I'm plugging in negative 1 for all these x's here. So negative 1 is going to go in all these spots. And so I guess something nice does happen in this next position. If I plug in negative 1, negative 1 plus 1 is 0. So that's all going to go away. And then I'm going to be left with, in this spot right here, I'm going to be left with 1 over 1. So this is just 1 times 1/5. And so what I get over here is 1/5 plus 2 times arctangent. Now, again, if I think about this, I get arctangent of negative 1 plus 1 is 0. So this is all going to be 0. So I get 2 times arctangent of 0. So what we could do is we could think about, hey, what is arctan of 0? And so as a quick aside, we would say okay, what do I have to plug into tangent in order to get 0? Right, so if we think about this briefly, so let's just go off to a new screen to think about arctan of 0 really quick. Right, so arctangent of 0 equals, we'll call it y, then the way to think about this is saying, hey, well, tangent of what is equal to 0, right? So what do I have to plug into the tangent function to get 0? We want these numbers to be between negative pi over 2 and pi over 2. And so if we remember, tangent is sine over cosine, right? So we have sine of y over cosine of y equals 0. So we can, another way to think about it. And so the only way that this is going to be 0 is if you have this numerator being 0. So another way to ask this question is, hey, when is sine equal to 0? And that only happens when y is 0. And so what we get here through this sort of process is that the arctangent of 0 has to be 0. Okay, so brief aside there. All right, so back to our work. And so this ends up being negative 2 times 1/5 is negative 2/5. And then 2 times arctan of 0 is just 0. Okay, so what we're left with is f prime of negative 1 equals negative 2/5. Okay. All right, so I'm going to pause here before we're not done yet, right? So we don't have the equation of the tangent line, but we did a lot of stuff, so I want to see if there's any questions at this point. Everybody's good? Why is arctan 0 again? Okay, so yeah, let's go back over here. So what we want to do is we want to think about this arctangent function, and the question we ask ourselves is, hey, when is tangent equal to 0? Okay, so we have to recall that we restrict our domain for arctangent to be negative pi over 2 to pi over 2. So if we think about the unit circle, right, so this is our unit circle. Up here at the top is pi over 2, and this is negative pi over 2. Okay, so when we think about the unit circle approach to this, what we're taking is we're looking at the x and y coordinates of the points on the circle. So all of the points on this circle have the form cosine theta comma sine theta, which means our x coordinates are given by cosine and our y coordinates are given by sine. Okay, so and in order to find tangent, what we're going to do, if I have tangent, right? So if we recall, we kind of talked about this a bit, SOHCAHTOA. So the tangent is opposite over adjacent in this, or you can define tangent of theta to be sine over cosine. So what I need to find is I need to look around on my unit circle and say, hey, if I ever take the y coordinate and divide by the x coordinate on the unit circle, when am I going to get 0? Right. So if I look over here, I'm going to sort of take x and y coordinates, and I'm going to take the y coordinate, I'm going to divide by the x coordinate, and I want the result of that to be 0. Okay. So when I look over here, right, all of these, it's never going to happen anywhere over here, because if we have our y coordinate is going to be some sort of negative number, and our x coordinate is going to be some sort of positive number. So none of these will be 0, and so it never happens here. It never happens on top. The only time that you're going to end up with a 0 in this is if you're right here, right, if your y coordinate is 0. Right? And so the only time, the input that happens, right, this is when we have 0, right? So if that top is pi over 2 degrees or radians, then this would be 0 radians. And then down at the bottom, you have negative pi over 2 radians. And so the only time that tangent of theta, which is sine of theta over cosine of theta, is going to be 0 on this interval is when that theta or this y is equal to 0. Right? So that's what you have to plug into tangent in order to get 0. Okay. Thank you. All right, so we get arctan is 0, and then if I come back over here, so we have this information, right? So we have a point, we have a slope, and what we want to do is put all of that together. So I'm trying to use my Blackboard skills here. All right, give us some more space. Let's see if we can place this. All right, so we have all this information, and what I'm going to do is I'm going to put all this together. So we have y, right? The equation of our line now is y minus y naught equals m times x minus x naught. And so if we come up here to the top, the piece of information that we get, right? This is our x naught, y naught, and this is m, right? So our slope is m, then our x coordinate is x naught, our y coordinate is y naught, and so what we get over here is y minus 0 is equal to negative 2/5 x minus negative 1. Okay, and so if we simplify this, we'd get y equals negative 2/5 x plus 1. Okay, and so then this, what we should be able to verify is that this down here is the equation of our tangent line. All right, so lots of work going on in this one, but if we jump over to Desmos, so let me switch my share here. Okay, so I think we see Desmos now. So here's our function that we were dealing with, 2x arctangent of x plus 1 over 5. Right, so it looks something like this. And then we have this point, negative 1, 0. So we want to find the equation of the tangent line. And what we said was it was y equals negative 2/5 x plus 1. And then, right, we can verify via Desmos that that's exactly what we want. Right, so we have this, our red curve is the original function, and then this would be the equation of the tangent line. Okay, so lots going on in that example. So I hope that it's useful as a review tool and to sort of illuminate some structure. So two big things, right? So we had a chain rule in there, we had a product rule, we had some inverse trig functions, and then we, on top of all that, we have the this equation of the tangent line, right? So that's all embedded in the structure of that one. Okay, so questions, comments, concerns? All right, so I'm not getting into anything from anybody, so let's go ahead and, I didn't mean to zoom here, but let's go ahead and we'll start in on section 2.7. So what's this one, 2.6? All right, so 2.7, this is gonna be the last section on our exam. So again, the exam will open up on Sunday. We'll have a week. You'll find 2 hours during next week to take the exam. And then the last material on this will be 2.7. So it'll cover everything from 2.1 all the way up to 2.7. So all of these sections in our book will be what the exam's over. So we've covered all of our derivative rules up to this point. So pretty much any type of function that you see, you're going to be able to take the derivative of. We can combine functions. We have all of the basic types of functions down. And so the one thing that we haven't covered is what if you don't exactly have a function, right? Is there still a way for us to, say, take the derivative or figure out what the slope of a function is? So in our book, if we can see this here, right? So the book gives us these pictures, and when you look at them, you would say to yourself, hey, that, this isn't a function because it doesn't pass the vertical line test, right? So you can't actually write down an explicit form of this, right? So you can't write it as y equals something. So instead, what we have is we have formulas that look something like this. We have what we call an implicit formula. And you're not defining a function. What you're doing is you're just defining a bunch of points in the plane that form this nice curve. Okay, so these things are used just like functions. And so one classic example of that is a circle. So anytime you have a circle, not a function because it doesn't pass the vertical line test, but you can define it implicitly with x squared plus y squared equals a number, right? So you can move this around. All right, so I guess the question becomes, well, if I were to sort of zoom in, right? So they're zooming in on this box and looking at this curve right here. How might we determine the slope, right? So if I looked at this curve just in this box right here, you would probably ask yourself, hey, I can probably figure out what the slope of, the tangent line is. So can I somehow find the derivative of this curve? And so this process of implicit differentiation is going to give us an answer to that question. So the short of this is what we're going to do is we're going to think about y as a function. And so when we take derivatives with things like 6xy, if y is its own function, then we would use a product rule on that term. And then if y is its own function, say for this y cubed, we would use a chain rule on that piece. Okay, so to start here, what we want to do is we want to look at this preview activity 2.7.1, and we're going to see if we can just look at the general form of these functions and see if we can take their derivatives. Okay, so this process is really going to help us out when we think about implicit differentiation. Okay, so to start us out here, what I want to do is I'm going to try to do actually, I'll leave A for you all. I'll try to do B here, right? So we can see sort of what this might look like. Okay, so I'm going to write this down. So B is we're going to take the derivative of x squared times f of x. Okay, so we don't know what f of x is, and so what we're alluding to here is that when we come back up with these equations, we don't know what y is. We can't figure out an explicit equation for y. So just like down here, we don't have an explicit equation for f of x, but we could still come up with an expression for this derivative. Okay, so let me jump back over. Okay, so we have this term, and we said, hey, I want to find the derivative of this thing, x squared times f of x. So the structure that we have to look at is we have a product, right? So we have this product rule, x squared times f of x. And when I take the derivative, everything outside of this, I'm going to use d dx to represent this operator. We're taking the derivative. But when I write out my formulas, I'm going to start to use prime, right? So I'm going to do a little prime for f prime. So this is a product, so I'm going to set up my product rule framework. And I'm going to go through, and anytime that I'm going to take the derivative of f, I'm going to write f prime, because I don't know what the derivative of f is. I'm just going to use that notation. And anytime I'm going to leave f alone, I'm just going to write f of x. Okay, so as we go through our first function, right, so our first function here is x squared, and then the derivative of f would just be f prime. I'm going to leave it just like that. And then we have our first function times the derivative of the second, and then we take the derivative of our first function and we leave the second one alone. Okay, so if I had anything that looked like this, the form of my derivative would be x squared f prime of x plus 2x f of x. Okay? And we're going to see a lot of stuff like this for implicit differentiation, but instead of f of x's, we're going to have y's. And so what I want to do is give you all a chance to try out some of these. Okay, so for a few minutes, we've got 8. So do you all have access to the book? Say A, C, D, and E. I just did part B. So let's go ahead. I'm going to put you all in breakout rooms for, say, I don't know, at most 10 minutes. And we can think through these 4, and then we'll come back together. Okay. So it'll give you 2 rooms. So it'll be 4 people in each room, so you can have a chance to think through these, ask questions, and we'll come back, and then we'll do some examples with implicit functions. Okay. So the rooms are open now. So Riley, I just saw your question here. If you're still here, so you can leave it in the first form. A lot of the time, we're going to end up simplifying for these ones because we're going to end up solving for that f prime or y prime that we get. So simplifying is going to be good in this case.
Okay.
Hello, how's everybody doing? We're all muted here. But okay, does everybody have access to the book and the questions that we're working through?
Yeah.
Yeah.
Yep, we got them. All right, so how did that go? It made sense or not at all? A little bit?
Yeah, it seemed pretty straightforward.
Okay.
At least for me, I'm stuck on D because the x squared is in the parentheses, but other than that, I've gotten the rest.
Okay, so x squared is inside, right? So that's going to be, so if you have an inside function, what kind of rule are you going to use?
Chain rule?
Yeah, right. So that would be a chain rule. Right, so when you think about that, when you have a chain rule, so you should have also seen that there's a chain rule on C and there's a chain rule on E. Okay, so C, D, and E all have a chain rule in there somewhere. Okay. So if you want, take another minute or two to think through these, right? A, C, D, and E, and try to share your answers with
It's a skateboarding game. It's like 15 years old.
All right. So I'm going to jump over to the other breakout room and see how they're doing.
Would be 1 plus 1 plus 2 f of x.
So it'd be 2 plus, or we could just combine them.
Yeah.
Are y'all thinking about this one? C?
We're on C. Yeah.
You said for C, you got 1. So if I just hear you correctly, you got 1 plus 1 plus 2 f of x,
Yeah.
like this. Yeah, Sam, you're right. This constant would go away, so this should be 0 here.
Wait, what for C, for the variable C?
Yeah,
Oh,
I didn't even realize that was a constant. I thought that was just another variable.
yeah. So that's gonna be a C. So the variable in these is gonna be given by this one right here. So it's telling you that x is your variable, and then everything else is gonna be constant, right? So this should be a 0.
So it'd be
1
zero,
is
yeah.
right.
Okay.
And then 2 f of x, but you're not, this isn't quite right.
wouldn't the constant just disappear? You just get
It
rid
would,
of
it would, yeah.
So
So
it'd just be 1 plus 2 f of x?
nope.
No. Okay.
So you're gonna think about it this way, right? So it's f of x squared. So f of x is your inside function.
Oh, so it would be 2f prime of x?
Yeah, right? So 2f of x times f prime of x. Right, so then this would have to be a chain rule here. Right, so when you put it all together, you get, this would be 0, c would go to 0, derivative of x is 1, and the derivative of f of x squared would be your outside function would give you 2f of x, and then you have to multiply by the derivative of the inside function for chain rule times f prime of x.
So then D would be kind of the same thing, but just the f prime of x squared and then times 2x.
That's right, yeah. So you'd have derivative of your outside function like this, leave your inside function alone, and then you'd be multiplied by the derivative of the inside function like that. Yeah. Yep. Okay, so I'm gonna go ahead and it seems like you're all doing fine here. I'm gonna go check in with the other room really quickly, and then I'll bring us all back together. It seems like we're doing fine on this.
Okay.
All right, so seems like everybody's doing pretty well. How are we doing in here? Did we share our answers?
We're still stuck on. Oh. I'm stuck on C. I know that.
On this one?
Like, yeah, I don't know how to do the f of x squared when the square is like on the outside. Where on the inside, it's like easier to see the chain rule, but on the outside, like I would get the same thing as on the inside.
So think about it like this, right? So you're going to have these parentheses that go around your f of x. So your inside function is f of x, and then your outside function is x squared.
Oh, the inside function is
Yeah.
okay.
So for C, when I take the derivative of a constant, right, that's going to be 0. The derivative of x is 1. And then what are we going to get for this?
Would it be 2 times f of x times f prime x?
That's right. Yeah. Yep, so that should be C, right? So what you're getting here is this is the derivative of your outside function, right? So this is your outside function. And then you're going to use the chain rule, and then you're going to multiply by the derivative of your inside function. Yeah. And so we talked about D a little bit, yeah. So did we reconcile did we see about part E as well?
I just got to E. I haven't.
Okay. So I'll give us another minute here, and then I'll bring everybody back together, and we can do this. Okay, so here in a minute, you'll see that little 60-second warning. and then we'll come back together. Okay, so it seems like we made some sense out of that one. So let's see. I'm gonna give everybody a chance. 1, 2, 3, 4, 5. Still missing 2, so give everybody a chance to get back here. And so what we're going to do is we're going to see how we can use a very similar process to determine the derivative of implicit functions. Okay, so the problem that they talk about in the book is this function x squared plus y squared equals 16. So if we wanted to find the derivative of that, so we'll go ahead and we'll walk through an example where if we look at that circle, how might we find the derivative of a point on that? Okay, and so, or the slope of the tangent line. So share. Okay, so I have our function up here, x squared plus y squared equals 16. And so this is a circle that has radius 4 and it's centered at the origin. And so what we're going to do is we're going to walk through this process and we are going to see if we can figure out what the derivative or the process for taking the derivative of something that's defined implicitly like this here. And so what we're going to do is I think a lot of the time it's helpful for students to replace all of your y's with f of x's. So you don't have to do this. It's not a necessary step, but sometimes it helps us remind that, hey, we're thinking about y as a function. And so we're going to have to do things like product rule and chain rule around. Okay, so this would be x squared plus, now instead of y squared, I'm gonna replace my y with an f of x equals 16. Okay, so I'm gonna look at the same structure, but I'm replacing my y's with f of x's, and then I'm gonna go ahead and take the derivative of this whole equation just like we did before. Okay, so I'm gonna go through and I'm gonna take the derivative of both sides of this thing, keeping in mind that we have this f of x squared, we have x squared. I'm going to take my derivative of everything with respect to x, just like we did in that warm-up activity. Okay, so going through here, what we're going to do is I'm going to take the derivative of x squared, which is 2x, and then I'm going to take the derivative of f of x squared, and so we just worked through that example, so this is 2 f of x times f prime of x, right, with our chain rule. And then the derivative of 16, that's just a constant, so if I take the derivative of that, I get 0. All right, so what we're interested in here when we're thinking about derivatives, we're always going to be interested in this f prime of x. So by replacing our y's with f of x's, we get this derivative that pops up. And so our job now is going to be to solve for this f prime of x. Okay, so the general process that we're going to work through is you're always going to solve for f prime of x. And step 1 is get all of your f primes on one side, and anything that doesn't have an f prime in it, put it on the other side. Okay, so step 1 here, we're going to, well, I guess step 1 was take the derivative. Now step 2 is going to be group your terms. Okay, so you're going to group your terms. So anything that doesn't have an f prime in it, I'm going to put on the other side. So what I get is 2f of x times f prime of x is equal to 2x. Okay, and then step 3, we're going to work through algebra to solve this for f prime of x. Okay, so in this case, we get f prime of x is equal to 2x over 2f of x. Okay, so simplifying a little bit, these 2's are going to cancel out. So this should be negative. Yeah, so I subtract the 2x over. And then what we get is we get negative x over f of x. And if we want to, then we can go ahead and swap back in our term here. We're going to swap back in y for f of x. So what I'm doing is when I'm thinking about the derivative of this implicit function, the slope across the whole curve is going to be given by this term negative x over y. Okay, so this would be the derivative or sort of the slope of the curve, if you want to think about it that way, as you're moving around the circle would be given by this term here. Okay, so one way that we can try and verify that, right, so I'm going to go ahead and shrink this down. So we have this work over here. What we're going to do is we could ask another a side question, something to the effect of, well, if I take a point on the circle, right? So let's say 1 comma square root of 15. So if I ask this question, at 1 comma square root of 15, what is the equation of the tangent line? Right, so if I'm going to draw the tangent line to this circle, I'm going to need, again, a point and a slope. So I'm going to pause for a second. Is it clear to everybody that this point right here, right, 1 comma square root of 15 actually lives over here on this curve? Right, does that make sense? So yeah, I'll get my chat up here. Yeah, it would be negative 2x, yeah. All right, so just quickly, right, so if you plug, so if this is x and y, if you plug in this 1 for x and you plug in this square root of 15 for y, it is going to be equal to 16, right? So it does satisfy this equation, so that point is going to be on there. So now what I want to do is go through this process and say, let's go ahead and just write our equation. Well, our point, right, our point is given to us 1 square root of 15. And then our slope is negative x over y, which is negative 1 over the square root of 15. Okay, so that's our point, and that's our slope. So what we should find is that if we write out this equation, y minus the square root of 15 equals negative 1 over the square root of 15 times x minus 1. If I look at this equation, we should be seeing a tangent line, right? So here's our equation. Let's go ahead and bring up Desmos and see if we can make some sense out of that. Okay, so share my Desmos here. All right, so here's our equation, x squared plus, x squared plus y squared equals 16, right? So here's our circle, and then this point 1 square root of 15 should be on there, right? So here's our point, right? 1 comma square root of 15. You can see it lies on the circle, and then if I type out our equation that we just figured out, y minus square root of 15 equals negative 1 over the square root of 15 times x minus 1, right? What we should verify is that, hey, look, this point is, right, actually on our circle, and this is our tangent line here. All right, so even though, all right, so despite that this isn't even a function, we were still able to figure out the slope, how fast this curve is changing at this particular point. And then with that information, we could even draw in that tangent line. Okay. All right, so I want to walk through another example. So something like this where we take an implicit curve and then we'll go ahead and find the equation of the tangent line. And so here's another implicit curve. So this is called an elliptic curve. And if anybody's into Bitcoin, this is the elliptic curve that I don't know if they use it anymore, but at one point in time they were using this elliptic curve in the background of Bitcoin. And so what we're going to do is we're going to see if we can do some calculus on this elliptic curve. So we have this equation right here. And let's see if we can figure out what is the equation of the tangent line at this point. Okay, so I'm giving you the point, and now what you have to do is take the derivative of this and then plug in your x and y values to get the slope. Okay, so let's take a minute here, try to work through this example, and then we'll do it together. Okay. Okay. So you see our picture. I'm going to bring up the board. See what we can do here. All right, so we got about 2 or 3 minutes left here, so I'm going to go ahead and jump in. Hopefully you've had some luck working through this one. So our first step, what I'm going to do is I'm going to replace all my y's with f of x's, and so I get something that looks like this: f of x squared is equal to x cubed plus 7, and with this expression, I'm going to go through and then take the derivative of both sides. Right? So what I'm expecting is there's going to be some f primes that show up through here, and then I'm going to solve for those f primes. Right? So just like we saw before with this f of x squared, I'm going to use a chain rule. So I'm going to get 2 times f of x times f prime of x. And then on this side, I'm going to get 3x squared plus 0, right? So that 7 goes away. And then solving for f prime of x, you get f prime of x is 3x squared over 2f of x. Or you can think about this as 3x squared over 2y. So sometimes it's helpful to go back and recall that, hey, that f of x is really our y. And so when we think about plugging in values, finding our slope, really this is our, remember that this is our xy up here. And so our x value is -1. Our y value is square root of 6. Okay, so what I'm looking for is, hey, what's the slope here? And so my slope is going to be 3 times -1 squared divided by 2 times the square root of 6. Okay, and so -1 squared is just 1, so this is 3/2 square root of 6. So putting this together, what I have is I have a point and I have a slope. And so we could go ahead and find the tangent line. Right, so I'm gonna put this over here. And so putting it all together, the tangent line is y minus square root of 6 equals 3/2 square root of 6 times x. Now it's going to be x minus -1, which is x plus 1. Okay, so this y minus square root of 6 is 3/2 times square root of 6 times x plus 1. This should be the equation of my tangent line. And then we can jump back over to Desmos and verify that. Right? And so we'll plug this in. So y minus square root of 6 is equal to 3/2 square root of 6 times x plus 1. And so what we can do is I'll go ahead and change the color so we can see it a little bit better. But we are still measuring the slope of that curve pretty well, despite this not being a function. Okay. All right. So we're pretty well into section 2.7 now, and so there's some more examples that the book works through. So for Friday, I think it might be helpful to go through this example, right? So there is a solution here. So try to read through this one. The interesting thing that's going to pop up is not only do you have a chain rule here, but you're also going to have to use product rule. And so what we'll do on Friday is we'll work through activity 2.7.2, and then we'll try to work through 2.7.4, right? So there's 3 examples here where we'll work through those. We'll end up finding derivatives, we'll find slopes of tangent lines, and there's some practice exercises down here as well. All right, so we're almost done with this section. We'll do more practice of these implicit derivatives on Friday, and then we'll have some time to, if people have questions about the exam. So again, we're 2 minutes over here, but if there's any questions that people have, I can field those now. So I'll give you a minute to type that, or feel free to just say it out if we have anything. I miss you all too. I enjoy our synchronous sessions, so I'm glad that we do these. It keeps me going. I like interacting with you all. But all right, so it doesn't seem like there's any questions, so we'll call it here. Have a great one. I'll see you all on Friday. Stay safe, stay happy. You too, Emily. See ya.